Hello class, this is a fourth example for mathematical induction. By now I hope you've memorized the steps involved. So now the only thing different for this is we're using factorial notation with our induction. It makes it only slightly more difficult, but if you keep your mind focused on what factorials mean, you'll see the process in this example. So let's get straight to it. As always, step 1, we let n equal the smallest value in the given domain. So for this one, it's going to become 1 squared plus 1 times 1 factorial is equal to 1 times 1 plus 1 factorial. This becomes 2 times 1 factorial is 1. This becomes 1 times 2 all factorial. That just becomes 2 equals 2. So it's true for n is equal to 1 since left hand side equals right hand side. I'm just going to leave it at that. Not 3. Step 2. For any integer k is greater than or equal to the same domain as what we've been given, we assume the statement for n equals k. So just to save time, I'm going to take this, and I highly advise you to actually also remove that third term because I think we get the idea. We assume true for this statement here. But instead of n, we're substituting in k. And from here, we're going to be working to prove we need to prove it true for n is equal to k plus 1. So from here, just showing you some solidarity, I'll write this out as well by hand. 2 times 1 factorial plus 5 times 2 factorial plus dot dot dot. It's going to become, watch how I'm going to write it, k plus 1 factorial, k plus 1 all squared plus 1. So there's that expression where I substituted k plus 1 there, times k plus 1 factorial is equal to, now substituting k plus 1 here, we get k plus 1. Substituting k plus 1 here, that's going to be k plus 1 plus 1. So in reality, we'll get k plus 2 factorial. Now this is what we need to work to prove to be true. Now it gets a little bit more difficult with the factorial notation, but watch very carefully how we're going to work this. We're going to take everything that we have, everything that we have here, and as we've always seen in the previous examples, there's always going to be one previous term to the one we've been given. Because if this is k plus 1, there must exist the term just before it. And the term just before it stops at what we made that assumption on. And as we've always seen in all of these, this expression is here. And we assumed that to be equal to this. So substituting that, we get k outside of k plus 1 factorial plus k plus 1 squared plus 1 times k plus 1 factorial. Now, here's where it gets a little tricky for some. This, oh wait, no, sorry. This and this are common factors. Think about this. It's k times everything here, and it's this times this one. If it makes it easier, I'll write it like so. I'm going to let, you don't have to do this one, but it's what's going on in my mind, just so you can see what I'm about to do. So let a equals k plus 1 factorial. So I'm imagining this entire expression as k times a plus k plus 1 squared plus 1 times a, because there they are. Take a look. Because of that, I can make this factorization. Take a look. I'm going to make a outside of k plus 1 squared plus 1. So I'm factorizing this expression out. So both of these are going to be factored out. So in short, I'm writing it like this. It's going to become k plus 1 factorial times k plus 1 squared plus 1. So everything here that I've written, you can skip that step, but if it helps, you can write that out. For this, I'm going to leave it out, and hopefully you can see how I made that factorization. Continuing this left-hand side simply becomes k plus 1 factorial, and inside the bracket we're going to expand it, plus k squared plus 2k plus 1. That's the expansion, so this here is that expansion, plus 1, because there's still that plus 1 inside that bracket. Collecting like terms, k squared first plus 3k plus 2 k plus 1 all squared. Now we can factor this into k plus 1, k plus 2. Now here's where it gets even trickier. In summary, it's going to become this. Take a look. Since these are all multiplication, k plus 1 factorial times k plus 2, that just becomes k plus 2 factorial times k plus 1. And I'll show you how we can prove that. Let's say we have 4 factorial. That's our k plus 1. And 4 factorial is equal to 4 times 3 times 2 times 1. K plus 2 is the next term. So that's 5 times. That's equal to just 5 times, like so. Well, isn't that the exact same as 5 factorial? Hence, k plus 1 factorial times k plus 2 is just k plus 2 factorial, which is what I did here. K plus 1 factorial times k plus 2 is equal to k plus 2 factorial. And there we have that equaling, where are we? That expression there. If we just rearrange it, Now let's just make this a little bit neater for ourselves. Whoops. This is equal to k plus 1, k plus 2 factorial, which is equal to the right hand side. And then making a last conclusion, thankfully I can use my iPad, copy this, and let's paste it, squeeze it in. I'm not going to copy out that statement because it'll be really difficult. So there we go. So by step 1 and step 2, the statement is true for all n is greater than or equal to 1, and that's the end of this example. So I hope you can see that the method still applies even for factorial notation, except that it just requires a little bit more extra step and more thought process. So I hope to see you in the next video where we do the last example. Hope to see you then. Best of luck.